In this video, I'd like to talk about compound inequalities, and there are two different compound inequalities we're going to talk about. And the first one is the OR inequalities. When we talk about an OR inequality, essentially what we're talking about are two different inequalities that are connected by the word OR. Now what this is going to tell us to do is include all solutions for both inequalities. So whether a solution works for one, the second one, or even both inequalities, all of these solutions are going to count as part of the solutions of an OR inequality. Or in other words, we keep any solutions that satisfy one solution or the other. It doesn't matter if it works for the first or the second or both. We're just going to keep all solutions for OR inequalities. And graphically, this simply means that we're going to keep all the points covered by both the graphs. So let's see this in action on a couple practice examples. Now when we see the word OR with two different equalities, the nice thing is that algebraically we're still just going to solve the two inequalities completely separately. In fact, if we want, we can even just separate these two inequalities with a line right down the middle, just recognizing that the OR means we're going to include the solutions from both of these. So for this first inequality, I say I have x minus 3 is less than negative 1. I'm going to solve for x, and I notice I need to undo the subtraction by 3 by adding 3 to both sides. This is going to result in our new inequality. So again, adding 3 to both sides. We're going to be left with x is less than a positive 2, negative 1 plus 3 being 2. Notice how I did not need to change the inequality sign, this less than symbol here, because all we did was add a positive value. Remember, we only switch the inequality symbol when I multiply or divide by a negative value. So here's our first solution, x is less than 2. And now we can go ahead and solve the second inequality. I have a negative 7x that's being multiplied. So to undo the multiplication by a negative 7, I need to divide both sides by a negative 7. So if I divide by the negative 7, I am left with just x on this left-hand side, but since we divided by a negative, I am going to switch the inequality. So if I look back at the original inequality, which was a less than or equal to, it's been switched now to a greater than or equal to sign because we divided by that negative. And then the negative 49 divided by negative 7 becomes a positive 7. So here's our second inequality. So when we write our actual solution out, then we recognize that both of these are true. Or in other words, I'm looking to keep all the values as x is less than 2, or I'm also looking to keep all the solutions where x is greater than or equal to 7. So I'm just going to graph both these inequalities separately now, and we're going to keep all the solutions for both of those. So for the first one, I'm going to go to the 2. And since it's strictly less than, I'm just going to leave an open circle at the 2. And less than 2 implies that I'm going to shade to the left. In other words, our solution set is going to be everything to the left of the 2. So all these negative numbers are going to be part of our solution, all the way down to negative infinity. So I'm going to shade everything right down to the arrow here. And now the second inequality, you see, is the x is greater than or equal to 7. And this is the important thing. Because it's OR, I'm simply keeping both sets of solutions. So I'm going to go up to the 7. Because this one is greater than or equal to, I'm going to fill in the 7. I'm counting the 7 as part of the solution. And then everything to the right is a solution because this is greater than or equal to. So essentially what we notice then is that the only spots that are not solutions of this inequality are between 2 and 7. These are the only numbers that aren't either less than 2 or greater than or equal to 7. Everything else is going to be a solution to one inequality or the other, making them a solution of the entire compound inequality. So here's a second example. Again, we're just going to solve both these separately. So again, if you want to, you can simply draw a line right down the middle, and really we're just going to solve these two inequalities separately. I notice I have two operations here. I have multiplication by negative 2 and addition by 7 that are happening to the x. I need to follow the opposite of the order of operations. So undoing the order of operations, I'm going to first deal with the addition by subtracting 7 to both sides. And what we notice is that this is then going to give us this new equation. Still have the negative 2x. I still have a greater than sign because I have not multiplied or divided by a negative, and then 15 minus 7 ends up being 8. So then, now that the addition's been dealt with, now I can deal with the multiplication by a negative 2. The inverse is division, so I can divide both sides by a negative 2. And I'm left with just x. Since I divided by a negative 2, right, see the operation was division by a negative 2 here, I do have to switch the inequality sign to a less than symbol, and 8 divided by negative 2 is a negative 4. So there's our first solution. Same thing on the right-hand side, this second inequality. I have 3x plus 1 greater than or equal to 10. I need to undo the addition before I deal with the multiplication, because we're doing the opposite order of operations, undoing the PEMDAS. So if I go ahead and subtract 1 from both sides, our new equation becomes 3x is greater than or equal to 9. Notice how I did not need to change the inequality because I have multiplied or divided by a negative. And then we need to go ahead and divide by 3 to undo the multiplication by 3. And I can now see that this gives me x still greater than or equal to. I did not divide or multiply by a negative. This was a positive 3. So it's going to stay x is greater than or equal to 3. So now that we have our two inequalities, again, I'm just going to graph both of them. I'm going to graph x is less than negative 4. But because I have that keyword or, I'm also now just going to graph the second inequality, x is greater than or equal to 3. And we're going to simply keep both solutions, one or the other. So for less than negative 4, I'm going to go to negative 4. Since it's just less than, there's no or equal to sign, there's no bar underneath, I'm going to leave this open. And less than implies that I'm going to shade to the left, because all these numbers here are less than a negative 4. And then the second solution, greater than or equal to 3. Because it's or equal to, I'm going to fill in the 3 this time. And the greater than implies that I'm shading to the right. So all these solutions here to the right are all greater than 3. So again, the only values that we see are not solutions to this compound inequality are the numbers in between negative 4 and 3. These are the only numbers that don't satisfy one or the other. Everything else is going to be a solution of this inequality. So one more or inequality. I've got some parentheses here, but again, the algebra has gotten a little bit more difficult, but we're still just going to be solving two different inequalities separately, and the or is just telling us, well, when we're done, we're going to have two different things that we graph, and we're going to keep the solutions for both of those. So first, if I have these parentheses, I recommend that we distribute the 3, so we don't have to deal with the parentheses anymore on this left-hand side. And this is going to give me 3x, distributing 3 times 2 is 6, still less than x. Now I notice that I have two x terms. I have this 3x term, and I have this x term over here. We need to somehow bring the x's over to the same side. It really doesn't matter how we do it. I think it might be easier, though, if we subtract this right-hand x from both sides. So if we do this, I'm going to have the new equation, 2x, when I do 3x minus x, plus 6, and since I have x minus x, that's just 0. Notice the inequality sign has not changed. It stayed less than the whole way through because I have not divided by a negative. So now if I want to continue getting x by itself, I can go ahead and do the opposite of the order of operations. So I need to deal with the addition by subtracting 6 first. And this will give me 2x is less than a negative 6. And then to deal with the multiplication by 2, we divide by 2. And the final form of our inequality is just going to be x is less than a negative 3. And notice the whole way through here, I never changed the direction of the inequality because not once did I divide by a negative value. So now the second inequality, I can again distribute to eliminate the parentheses. So distributing the negative 4. This inequality is going to become negative 4x. Negative 4 times 1 is a negative 4, less than or equal to a 20. So now all we need to do is a little bit of solving here. So I'm going to first, again, opposite of the order of operations. I need to deal with the subtraction before the multiplication. I'm going to add 4 to both sides. And this is going to leave me with the new inequality, negative 4x less than or equal to a 24. And now that the subtraction has been dealt with, now we can deal with the multiplication by negative 4 by dividing by negative 4. And as a result of that division, I am just left with x. Because I divided by this negative 4 here, I do have to change the direction of the inequality. So it switches to a greater than or equal to sign. And then 24 divided by negative 4 is a negative 6. Okay, and here we see one of our unique situations. So I have two different solutions, x is less than negative 3, or x is greater than or equal to negative 6. And here we see a unique thing happening. If I graph the first inequality, we do this pretty easily. Less than negative 3 means that I would be open at negative 3. And the less than implies that I'm simply going to shade everything to the left. So here we go. I'm going to shade everything down here to the left. So far, so good. Here's where things get a little bit different, though. My second inequality is x is greater than or equal to negative 6. And here's where we notice something different happen. I'm going to do this in a different color to emphasize. Negative 6 is right here. And if I do greater than or equal to the negative 6, I notice that I'm going to have a closed circle at negative 6, but the greater than or equal to is telling me to shade to the right, because that's the greater than or equal to sign. All the sides to the right are greater than a negative 6. When we do this, though, what I notice is that they overlap in such a manner that I've actually covered in the whole number line. There's not a single value here that is not shaded. And since it's OR, I don't want to remove any part of these solutions. I want to keep all the solutions. So essentially what this is telling us then, this is a special case here, what this is really saying is that all values are solutions. So all values are solutions. And this is a unique case, but we can see this sometimes with the OR. When they overlap in this manner, it is possible to highlight the whole number line, and that just means, not a big deal, that all values are going to be solutions. Okay, second type of inequality now are the AND inequalities. AND inequalities can commonly be written with two inequality signs in three parts of the equation. Or in other words, they're kind of meshing two inequalities together into one statement. And here's an example of it here. Negative 2 is less than x plus 5, which is less than 3. What I want to emphasize to you, though, is they write it this way because it's easier to solve, but it is still two different inequalities, and I can write it out for you. First is this inequality on the left-hand side. So basically, if I just look at the left half side, there's this first inequality, negative 2 is less than x plus 5. That's the first inequality that this is saying. The second inequality is then just looking at the second right-hand side. So, and the second inequality would be x plus 5 is less than 3. So this is a common notation. Whenever I see two different equations meshed together like this, it's implied that the word is AND in between, and there are still two inequalities. So what we want to focus on now is what this word AND means. And we notice for AND inequalities, this is going to be different. Instead of keeping everything like we did with the OR, for an AND inequality, we are going to only keep solutions common to both of the inequalities. So, in other words, we're only going to keep solutions that show up for both. This is easiest to see when we graph, because the key thing is that we're only going to keep points where both graphs overlap. And we'll see this in a problem in just a second. So again, to emphasize that difference, with OR inequalities, I don't care if they overlap or not. I'm going to keep all the solutions. But for an and inequalities, I'm only going to keep the solutions where the two graphs are going to overlap. It has to satisfy both inequalities for us to keep this solution. So let's see this in action. Here's a simple one, and again, we do notice that this is two inequalities. If you want, you can split them up right away into the two inequalities like I showed you on the last slide, but it's actually faster if we keep it as a single compound inequality like this. What we can do is if I just break this up into three parts, basically draw a line down at every inequality sign, I can speed up the solving process if I just do the same operation to all three parts at the same side. Recognizing that what I really want to do is solve for this x in the middle. I'm trying to get this x in the middle by itself. So I'm going to solve just like always. If I wanted to get x by itself, the first thing I have to do is undo the addition by subtracting 4. But here's the thing that's different. There's not just one side of the equation now. There's a left, there's a right, and there's a middle part of the inequality. So I'm going to just subtract 4 from all three sides. And this is where keeping your organization in line is very important. So now I can just rewrite all three parts of the inequality. So negative 2 minus 4, this becomes negative 6, still less than. In the middle, I'm just left with a 2x, and then less than 12 minus 4, which is 8. So notice how I did the same operation to all sides of the inequality with the idea of getting x by itself. And I'm going to keep doing this. So now I need to undo the multiplication by 2 so I can get x by itself. Inverse of multiplication is division, so I'm going to divide all three parts of this inequality by 2. And this is going to give us our new inequality statement. So negative 6 divided by 2, that's negative 3, which is less than x, which is less than 4. And I've seen now that I've actually solved it, and I have our two inequalities. So the solving process took a lot less time here. We only had to do it once instead of 2 times if I broke it up. Now I can simply write the two inequalities. So here's my first one. Now notice I would like to write this with the x on the left-hand side because that's what we're used to. So this is really the inequality x is greater than negative 3. Notice how in both cases it's pointing to the negative 3 and it's eating the x. So both times it's eating the x, pointing to the negative 3, pointing to the negative 3. So there's our first inequality. And then I can write the second inequality, which is just the second half. Or in other words, this x is less than 4. So and x is less than 4. Now when we graph, remember, because this is an and inequality, I only want to keep the parts that overlap. So here's where we almost have to do a couple steps with our graphing. What I recommend for and inequalities is actually starting by graphing above the line, looking at where they overlap, and then using that to graph our final solution. So for greater than negative 3, I'm at negative 3, it's open, and because it's greater, I'm shading to the right. So our rough graph for greater than negative 3 looks something like this. But again, I only want to keep the parts that overlap. So let's see what overlaps here. If I then look at the less than 4, I can see that less than 4, well, that occurs at 4. Again, it's open. But because this is a less than sign, I'm now just going to be shading to the left. So here's our second graph. Now if this was an OR inequality, we'd see that the entire number line was shaded and it would be an all solution case. But because this is an AND inequality, I only want to keep where it's overlapping. And I notice it's only overlapping between negative 3 and 4. Or in other words, only between here, negative 3 to 4, do I see the red and the blue graphs overlapping. So I'm just going to graph this as my final solution from negative 3 all the way up to 4. And what this means is that the only solutions of this inequality are going to occur in between -3 and 4. And when you're done, if you want to erase the other two shading that you used to get your final solution, that's fine. Or if you want, you can even keep those there. That's fine as well. So if you want to leave those lines in there to kind of show your work about how you got that shading, that's fine. But recognizing that the green value on the number line is our only actual solution. So here's another inequality. Again, I notice it's an and inequality because they wrote it as a single statement. So I'm going to go ahead and split this up into 3 parts, right, drawing lines right down the middle of each inequality. I'm trying to solve for x, so the first thing I have to do is undo the subtraction of 3. So I'm going to add 3 to all 3 parts of the inequality: the middle, the right, and the left-hand side here. Again, very important to stay organized during these. So this is going to leave us -5 plus 3 is -2, less than a -2x, which is less than 14 when I add the 11 and the 3. Notice how I haven't changed any inequalities. We're still looking for that. I haven't changed any yet because we have not divided by a negative value. My next step, however, I do have to divide by a -2 to undo the multiplication by 2. So here's where we have to be really careful. A lot's going to be going on here. When I divide all of these by a -2, things are going to change a little bit. First thing I have to do is change the direction of both signs because I am dividing by a negative. So just like before, we're flipping the signs. -2 divided by -2 is 1. I have x in the middle. And then 14 divided by -2 is a -7. So again, now at this point we can write our 2 inequality statements. So here's my first one. Again, I like to write it with x on the left-hand side just to make it a little bit more clear. So if I start with x, I need the inequality sign pointing at x, just like we see up here. Right, we notice how x has the inequality sign pointing at it. So I'm doing the same thing down here. So really that's the inequality x is less than 1. Now what's our second inequality? Well, and let's look. The second inequality is right here. And that's already in the right order for us. And x is greater than a -7. So if we graph these, the first inequality, I'm at 1. Again, I'm going to do it above first to see where the overlap is. It's open because it's strictly less than. And the less than is implying that I am shading to the left. So my solution is going to look something like this. The second one is greater than -7. So I'm going to go down here to -7. It's open again because it's not greater than or equal to, just greater than. And then here's our shaded solution, everything to the right, because it's greater than. But again, our final solution is only where they overlap, and I see them overlapping between -7 and a +1. So I can go ahead and say, well, that means my final solution is at -7 to +1, only in between where they overlap. Good, and again, notice a couple things to point out here. I've kept these as open circles. Notice how I haven't changed the endpoints where they're overlapping. And the final solution in this case is only the red graph, only where they overlap. So notice how that's the one I've drawn on top of the actual number line. Final example problem. I've actually written this one out with the and symbol already. If it's in this form, instead of trying to combine it, especially when I see 2 different equations, there's really no easy way of combining these 2. It's easiest just to treat this just like we did with the OR ones. Solve them separately. But we are still going to graph it like an and inequality, so in other words, only keeping where they overlap. So starting on the left-hand side, I'm going to solve for x. I have to deal with the +3 before the multiplication. So if I subtract 3 from both sides, that looks to me like I'm left with 2x less than 2. Then I can deal with the multiplication by 2 by dividing by 2. Which means our final equation is just x is less than 1. And notice how I never had to change the inequality sign because I never divided or multiplied by a negative. So on the right hand side, I have to first deal with the positive 5 before I deal with the multiplication by negative 4. So I'm going to subtract 5 to both sides. This is going to give me the new equation, or inequality rather. Negative 4x less than or equal to negative 24. I haven't switched the sign yet because I haven't multiplied or divided by a negative. But here in this next step, to get rid of the negative 4 that's being multiplied, I have to divide by a negative 4. And here, since we did divide by a negative, I am going to have to go ahead and switch that sign from a less than or equal to a greater than or equal to. And notice that that's going to change to a positive 6 when I divide. So here we have our final inequality. X is less than 1, and second inequality, x is greater than or equal to 6. Now keep in mind, because this is an and inequality, I'm only going to keep where they overlap. So I'm going to go ahead and graph both these separately. First, less than 1. I'm going to go to the 1. It's strictly less than, so I'm going to leave this open. And the less than implies that I'm shading to the left. Right, notice all those numbers that I've just highlighted here are in fact actually less than the 1, right? All those negatives. The second inequality, again I'm going to do this above because I'm looking for where they overlap. It's greater than or equal to 6. The or equal to implies I should be shading in, and then the greater than implies I'm shading to the right. But here's an interesting case, another special case here. I notice that there is no point where these two graphs are overlapping. So in other words, there is no point where a value satisfies both less than 1 and greater than 6. And this makes sense. It's impossible to be less than 1 and greater than 6 at the same time. So this is a special case. And in other words, this is what we call a no solution case. So no solution. Okay, so at this point, I have 4 on your own problems I'd like you to try for the rest of the homework, and then we'll check in on this next class.